you remember last time, 2 days ago, we stopped. Yes, so we stopped at this point. So we basically completed the load assessment. So we found out that on our structure, we can have 6 different types of loads. So this is the G1 is the self-weight of the structure. G2 is the permanent load. Then QS is the snow load. And then we have either QW1 or QW2, which is the effect of wind, according to the old Italian regulation. You may be aware that with the new circolare, with the new document explaining better the technical regulation for construction, the wind load has become more complex to calculate. I was talking with Dr. Shomenta. She told me that with the new one, basically we should do something, when you have to design like a single story building, you have to do something like a 90 load combination, which is something a bit crazy to me. Because the new document is based on the Eurocode 0, actually Eurocode 1, where of course dealing with wind is a bit complex because it considers several possibilities. So we will have another, you will have another hour, even more than 1 hour with Dr. Shomenta, see how to do it, how to deal with the load, because of course, how to deal with the wind, because of course 90 load condition only from the wind, me seems a bit too exaggerated. So with the old one, we had 2 basically. If you remember, we had one load condition was when you had something like this. So you have the external load and we have a pressure inside. And then the other one was with distribution outside in some way. And inside we have a pressure instead of suction. Well, suction and pressure. So we have 2 load conditions. So in the end, we have one of the 2, QW1, perhaps it's downwards, and the other 2, QW2 is uplifting. Now I can't remember which one, we'll see in a few minutes. So one is downwards, the other one is uplifting. So we have these 2 possibilities. But of course we have either one or the other. We can't have both of them simultaneously. So we need to choose either one or the other. And then we have the maintenance load. So this is the load that we have to deal with. If you remember last time, we were almost 7 o'clock on Monday, I asked you, what do you think? If you were to design this structure made of reinforced concrete, which load condition would you have to consider? So of course, this is the fundamental load condition, but you have 1, 2, 3, 4 variable loads. So in that case, which load condition would you have to consider? Can we do it together right now to see if you remember how to deal in the case of non-timber material? So let's start to write F1. First load condition would be, can some of you help me? Now we're talking about what we are supposed to know, because what we discussed in reinforced concrete design, we're not talking about timber now. And then we'll see how many more we need to add for timber. Okay? So, okay, we start. Gamma G1 times G1 plus gamma G2 plus. Yes, but then we need to choose. Which Q do we choose now? We choose with snow, for example, so the snow load is the basic variable load plus gamma Q, then let's say C0 times QW1, so this would be C0W plus gamma Q times psi 0 C and then QC. Okay? So this would be the first load combination. It's clear? Why we haven't put inside here 2W2? Either one or the other, okay? Because there are two different load conditions. Okay, they cannot be together, either one or the other, okay? So this is the first load condition. Then second one, F2 equal. First part, the same, so we can do this way. Then this QW1, for example, plus gamma Q psi 0 S QS times gamma Q plus gamma Q psi 0. What is missing there? C QC. Okay? Then, yes.
Is this what is for the reinforced concrete? Or?
Yes, where now I said what would be the load condition that we would have to consider in case of a reinforced concrete structure. And then we will see there are some more to consider in the case of timber. Okay? Then, next. F3.
The reaction is QC.
Gamma Q QC. And why always okay, yes, this is as well. QC plus gamma Q psi 0 W what do we call it? QW1 plus gamma Q psi 0 S QWS. Okay? Finish?
Gamma, the same more gamma Q. More gamma Q.
Which Q? C plus I would like to write this one later. We'll leave it down here to make more in order. Gamma Q, QC plus
gamma QW1
psi 0. What's the difference now?
for QW2.
Yes, it's better. Plus gamma Q psi 0 QS. What else do we need to do? We finish everything?
No, as a base action, W2.
Yeah, so F4. So we need to repeat again this one. So gamma Q QS plus gamma Q, here we put psi 0 W QW2 plus psi 0 gamma Q QC, and then F5 still miss gamma Q QW2 plus gamma Q psi 0 S QS plus gamma Q psi 0 C QC. Okay? So 6 load combinations. Okay. of these 6 load combinations, when we are designing the reinforced concrete, which one do we choose? Do we choose all of them, or what do we do now? First, of course, we need to replace the value of the gamma G, gamma Q, based on the Italian regulation, for example. But of course, once we have replaced all the values, the right values, actually, you remember to put the right value there. Because for gamma G1, gamma G2, and gamma Q, the regulation gives you 2 values. One value for favorable loads, another value for unfavorable loads. So for example, if we start from the first one when we have the snow as a basic load, which value should I use for gamma G1? 1, which is for favorable action, or 1.3, which is for unfavorable loads?
1.3.
Why?
Because this node is unfavorable.
Because snow is oriented downwards, and then if you have a permanent load, this is going to increase the effect due to the snow. Here we are talking about the simplest, well, simply. Now it depends, of course, on the static scheme, but if we are talking about not continuous beams, for sure, it will be always favorable, and it's unfavorable, and then we have to take 1.3. So this would be 1.3. Then gamma G2 is 0.8 if it's favorable, or 1.3 if it is unfavorable. So in this case it would be, say, 1.3 or 1.5, depends if the load is well defined or not. Gamma Q QS is 0, 1.5, so what do we put here? 1.5. Then QW1, you need to check, was QW1 positive or negative? So was it pressure or suction? If you can look at the notes before. Good, because I can't remember now. It's Q was a pressure. So if QW1 is a pressure, which value of gamma Q we should put here? Unfavorable, so 1.5. And then we need to find the size 0 coefficient. Size 0 coefficient would be, depending on the load condition, it could be 0, could be 0.5, 0.4. It's given by the regulation. Okay? And then maintenance, again, unfavorable and so on. Okay? So if QW1 is positive, so it's pressure, it means that QW2 is negative. So in this case, for example, let's talk about this load condition here, where we have QW as a basic load condition. Here, which coefficient should we put? So when we consider QW2, which is uplifting as a basic load, which value should we put here for gamma G1 plus gamma G2? So this one, for the set weight, this one is favorable in this type, because it's opposite. This is uplifting, this one is going down. So for here we would give 1.0. And for gamma G2, it's a 0.8, either 0.81, so it would be a 0.8 in this case. Then this one is 1.5. And then this other two, gamma Q ranges between 0 and 1.5. So QS and QC, how are they oriented, QS and QC? Are they uplifting or they are downward? Downward. So it means that which value gamma Q here and here?
1.3.
No, gamma Q is between 0 for favorable to 1.5 for unfavorable. So is QS favorable or unfavorable?
0.
So 0. So 0 and 0. Okay? If you remember, we are repeating what we discussed in the previous course about reinforced concrete design. This was actually basic of mini state design, not the basics of reinforced concrete. Okay? So, okay, we calculate, we do all this calculation. In the end, we end up with 6 numbers. What do we do with these 6 numbers? So I need to design for all these 6 nodes that I find out.
Only for the large value.
Only for that?
Large value.
Only for the greater value. If I have 6 values, say from, let's say if I have 6 positive values from, let's say, 20 to 120, I just take a load condition with the greatest value, with 220. This one is the governing design load for my structure. Then I can forget about all the other 5 load combinations, just go on with this load condition. I design for this load condition, and that's it. Okay? Any doubt about this? So, is everything clear here? Are we sure? Okay. So that was the story for reinforcement. But now we're talking about timber. Is that enough for timber? No. What is missing for timber? Why is not enough for timber? Those 6 load conditions there.
We need the K mode.
We need to consider that for timber we have also a K mode, which is going to vary among load conditions. And it's going to change between different values. It's going to affect also the strength demand, also the strength capacity. Sorry, not only it's going to affect also the strength capacity. So in the case of timber, we need to consider also some additional load conditions. Which additional load conditions should I consider for timber? We need to start removing variable loads. So for example, to say, okay, now I do another load condition, I do more load conditions without QC. All the different load conditions without QC. How many possible load conditions are without QC? You have G1, G2, then, for example, QS is the basic value with 1.5, and then I have QW1, and that's it. Okay? Then, another one, G1, G2, now I put QW1 as a basic value and QS as a combination value. Finished? No, because I have also QW2. So I need to do another one, G1, G2, QS as a basic value and QW2 as a combination value. Another one, G1, G2, QW2 as a basic value and QS as a combination value. Okay, so 4 more, let's say, plus 4, where I take the, we said, QS as a basic. No, sorry. I said 4 without QC. Okay? Then what do I need to do? Another 4 without what?
Not considering snow.
Without QS.
Maybe moderate, not considering W1 or W2.
Then let's go to see. Then if I don't consider QW1, how many possibilities do I have? Well, if I don't consider QW1, I should also not consider W2 because it's either one or the other. So I have QS as a basic and QC as a combination, or QC as a base and QS as a combination. So another 2. Okay, finished? We need to do something more. Why do we do all this combination? Because I remind you that we will have then to calculate the K mode factor and the ratio between the load and the K mode factor. And the K mode factor is different when you change the different load conditions. because the gate mode factor will have different value for each load, for each action, and then you have to take the minimum one. So for example, if here you have 0.6, 0.9 and 1.1, here you need to take 1.1, the maximum one. And as you start taking away the load, you basically increase the K mode. If you increase the K mode, you reduce the strength. Okay? In order to find out which one will be the governing design condition, we need to find out the ratio between the load condition itself and the K mode. And so, to do so, we need to find out all the different load conditions. So, and we finish here. Now, what do we need to do now? Before we are taking away one variable action, now we need to take away two variable actions. So, for example, I take away QS and QC, or both. So I consider only one variable action. So I will have how many load conditions? Two. One with QW1 as a basic one, another one with QW2 as a basic one. So another two without QW1, QW2. Then, if I take away both QC and QW1 and QW2, we have only one with QS. Okay? One. So here we said that before we said two because we take away. Why did I say two here? We said we take. Okay, we say initially we take away QC and QW. So I have only one actually, not two. I don't know why I said two. Because now we are taking away two variable load conditions. So we take away QC and this one. Because the case with QS and QW1, for example, was already considered before, if I remember well, right? So now I take away this and this, I have only one here, would be one with QS, then I have one with QC, and then two, because one with QW1 and one with QW2. So basically I have P plus 2. This one was without QW1 and QC. The second one was without QS and QW1. And the last one, 2, is without QS and QC. And then I take the final load combination where I take away all the variable loads. In the end I have only plus G1 and G2, that's it. Okay, are we missing something? Hopefully not. So in the end, if everything is correct, if we ever miss something, we have to consider 6 plus 10, 16, 20, 21 load conditions to have all the possible combinations. Okay? Now let's go to C because it's easier to see here. So we start again from the beginning. First one, you see here all the loads. We choose here the QW1 and we choose the snow as a main variable action. Then we choose the QW1 as the main variable action, and then QC as a main variable action. Okay? Then we repeat exactly the same by replacing QW1 with QW2. So we have another 3. Similar. Okay? Then we start taking away variable actions. So we take away, for example, here we take away QC. Okay? 2, because here is QS, the basic, here is QW1, the basic. Then we repeat with QW2. Then we take away the wind. So we have two load conditions, QS and QC. When we swap the basic value. Then we take away QS. So we have QW1 and QC. And QW2 and QC. Then we consider only the snow, only the maintenance, only the wind in one direction or the wind in the other direction, in the end only permanent load. Okay? So strictly speaking, we have to consider all the different load conditions with and without all or some of the variable actions. Okay? Any question about this is clear? Yes. There may be a small mistake here. Because try to check, because I remember yesterday evening I found a mistake. Maybe it's the number 4. Yes. Because after I corrected, but of course this was too late for you. Yeah. No, right. Yeah. So please correct. Here is QW2 rather than QW1. Okay, number 4. No, exactly. You're right. I found yesterday night I found this mistake when I was revising. Okay, have you corrected everything? You have to correct here this one. The substring is 2 rather than 1. Okay, so other questions? Is clear everything what we've done? Bit boring, as you can see. But strictly speaking, this is what we have to do. Okay? Good. Now, we have to repeat. Here will be easier, fortunately, but we have to consider also the load combinations for serviceability limit states. So we understood now for timber structures and for steel structures, it's also important to check serviceability limit states. Important to check deflections, so spontaneous deflections and final deflection. So for serviceability limit state, we have to consider the characteristic or rare load combination, which is this one that you can see here. So also here, of course, if you have different variable action, also here you need to rotate the different variable action. If you have 4 variable action, you have to consider at least 4 when you are rotating the variable action in the position of the base, when you consider them as a basic load conditions. Fortunately for serviceability limit state, we don't have the problem with the K mode. So in this case, we don't have to consider only, only one variable load, then 2, then 3. In this case, we do like we are more confident to do for reinforced. It's just a matter of finding the maximum value of the load condition, because we don't have the K mode factor. So we have to calculate short-term deflection. The short-term deflection is given by the Italian regulation. The Italian regulation gives a limit of the short-term deflection due only to the basically variable loads. So in this case, we need to consider only the variable part of the characteristic load condition, basically the part without the permanent load and without the favorable loads. So QW1 in this case is the favorable load. Can you check this? Because I thought that before you told me QW1 was unfavorable. It should be QW1 should be the one, the load basically upwards. Is that right? The other one I need to correct here.
Level 1 is not pressure.
Is the pressure number 1 or is
No, sorry.
okay, so W1 is the suction, okay? So just take a note, before, what we said before was wrong actually. So we need to swap QW1 with QW2. So before, when we put this number here, we were assuming that QW1 was a pressure, while instead, in the reality, at least in this exercise, QW1 is a suction, okay? So, when we calculate the short-term deflection due to the part of the variable of the characteristic load combination, we need to remove the permanent loads and we need to remove the favorable, we need to remove the favorable variable load, so QW1, which is a basic assumption. So we need to consider only QS, snow, maintenance, and wind downward pressure. So in this case we have only 3 load combinations. We have the one with QS as a basic action, the one with QC as a basic action, and the one with QW2 as a basic action. Okay? Then we need to calculate the final deflection. So the deflection in the long term. The deflection in the long term is given by the sum of 2 components, the instantaneous deflection and the creep deflection. So for the instantaneous part, without the favorable loads Qw1, we have 5 loads, G1, G2, QS, QC, QW2. So we need to consider 3 load combinations like before, but in this case we need to add the 2 permanent actions. Because when we calculate the final deflection should be calculated under the entire characteristic load combination, while instead before the instantaneous deflection was calculated only under the variable part of the characteristic load condition. So in this case we have to consider these 3 load combinations, 1, 2 and 3 when we change the variable action. Then we need to calculate the quasi-permanent load combination. Quasi-permanent load combination is the one that you can see here. So it's basically the permanent loads plus the quasi-permanent values of the variable actions. And so the final, the long-term deflection calculation can be done by ignoring the favorable loads, so QW1. We have to consider basically these 5 loads, G1, G2, QS, QC, QW2. We have only one load combination in this case. So in this case, we have G1 plus G2 plus psi coefficient psi times QS plus another psi coefficient times QC plus another psi coefficient times QW2. Okay? So for the time being, this is just an introduction, because of course then we need to make the calculation of this value for the different structural members. Okay? So in general we will have to follow this principle here for the purlins, so for the design of arcareccio, and also for the design of the truss. But then of course the load will be different, because for the purlin the value of the load will be different compared to the value that we have on the truss. Okay, but the principle, so the list of the load combination will be the same in all the cases. It's clear this? Again, any question about what we have seen so far? It's a bit awkward, I would say, but this is what we should be doing. Okay, so now we start doing the design, starting from the purlin. So purlin in Italian is arcareccio. So how do we design a purlin? So first we need to calculate the design load at ultimate state, so the governing design load at ultimate state, and then the strength demand. So first we need to choose the most critical load condition using this principle that we defined before, and then we need to solve the beam by calculating axial force, bending moment diagram, and shear force diagram. Then we need to design the purlin for biaxial bending. So in this case, the purlin, since we have a double pitch roof, the purlin will be inclined. So it will be subjected to biaxial bending, flessione deviata. Okay? Then we will have to do the serviceability limit state design load, so to calculate the serviceability limit state design load and calculate the short time deflection and compare with the limits given by the regulation. Then to calculate the final deflection, so the deflection in the long term, and to compare with the limits given by the regulation. Shear strength at ultimate limit state, so another verification of ultimate limit state. Bearing strength, which means the length of the support of the beam in order to avoid compression perpendicular to the grain. And last but not least, lateral torsional buckling. Okay? So this is the sequence of checks that we have to do it on the purlin. So we start from the first point. Calculation and choice of the governing load condition among those 21. Okay, so first of all we need to calculate, of course, the value of the G1, G2, QS, and the QW1, QW2, and QC. So to calculate the permanent loads, first of all we need to have an idea about the spacing between the purlins, because we need to calculate the tributary width of the purlin. So you see here the spacing of the purlin is 0.5 meters, so 50 centimeters. So the non-structural permanent load was assessed the day before yesterday, was 0.9 kN per square meter. And so we can calculate the uniformly distributed load of the purlin, which would be the pressure 0.9 times 0.5, so 0.45. So this is the non-structural permanent load. Then we need to calculate the structural permanent load. Structural permanent load is the load of the planks, so this layer of planks that we have above the purlin. We assessed yesterday this load was 0.15 kN per square meter. So we need to multiply 0.15 times 0.5, the tributary width of the purlin, 0.075 kN per meter. And then we need to calculate the self-weight of the purlin. Self-weight of the purlin was calculated yesterday, the day before yesterday was 0.12. If we sum those two values, 0.075 plus 0.12, we get 0.20. So, sorry, we have to do 0.15, 0.75. Yes, correct, yes, 0.195 is more or less 0.12. Then we need to calculate the variable loads. Snow was 1.14 kN per square meter. If you remember, all the loads were basically referred to 1 meter of inclined surface in such a way that we can sum all of them together. Otherwise, we were unable to sum the snow, which is per square meter of projection, with the self-weight, which is per square meter of inclined surface. Okay, so yesterday we transform all of that in the value per square meter of inclined surface. So, snow 1.14 times 0.5 is 0.57. Maintenance is 0.5 times, again, the spacing, which is 0.5, 0.25. The wind, QW1Z was minus 0.5 times 0.5 is minus 0.25. QW2Z is plus 0.09 times 0.5 is plus 0.04. So here we have two components, because if you remember, the wind acts in this direction. So for the wind there is a component, vertical component, and then there is a horizontal component. QW1 is this component here. And then we have for QW2 QW2 was this vertical component here. So negative suction and positive pressure. Okay, so those are the combinations, are ultimate limit state, serviceability limit state. Now we start with the ultimate limit state. This is the load condition we have to consider. Here are the coefficients. So you see for self-weight 1, 1.3. For permanent non-structural load 0.8, 1.5. So 0.8 is favorable, the 1.5 is unfavorable. And variable is 0 and 1.5. So those are the values that you need to consider within these combinations. Then we have the coefficient size 0. 0 for maintenance, 0.6 for wind, and 0.5 for snow. So those coefficients are 0 here. Those are the values of the load. And then we need to replace those values of the load in these 21 load combinations together with the appropriate value of gamma G, the gamma Q, and together with the appropriate value of size 0. Okay? So, and we need to remember that the K mode are different. So G1, for the K mode for G1 and J2 is 0.6, for QS and QC is 0.9, and for QW1 and QW2 is 1.1. Now, again, those are the load combinations that we saw before. Now it's a matter of replacing the variable with the numbers. So you can see here the calculation of the different load conditions from 1 to the last one. And then, of course, out of this load condition, if you have a look, the maximum one would be, for example, the fourth. So the fourth, the ninth. So the fourth and the ninth are the maximum ones. Maximum is a value of the load. But then we know that the most critical one is not the one which is maximum in terms of load. It's the one which is maximum in terms of ratio between load and K mode. Okay? So, now we calculate the K mode, this ratio. You see, load combination 1, 1.8. K mode 0.6, 0.9, 1.1. So, you need to take the maximum one. Because if you remember, if you have a load combination given like different loads, you need to take the maximum K mode. So for this one, we need to take 1.8 and divide by 1.1, you get 1.64. So you do this calculation for all the different load combinations. You find out that the most critical one, you see, is the number 11. Number 11 has two also number 17 has 2. So, despite of those load conditions not being the maximum one, so the one with the maximum value, those are the most critical ones because the K mode here is lower. So this means that from here we have to continue in our design by using only load combination, either load combination number 17 or load combination number 11, because they both are the same value. Okay, so we just take the value, which will be 20. Sorry, it's 2, but 2 is the value divided by 0.9. So the value we need to consider is 1.8. So 1.8 kilonewton per meter. So this is the governing design of 1.8 kilonewton per meter of distributed load. K-bond coefficient 0.9, we said. So, strength demand, we have a simple supported beam. This is very simple to solve. So we find out immediately that the restraint reaction is 1.8 times 5 times the length divided by 2, so 4.5 kN restraint reaction, which is also the maximum shear as a support. Then we calculate the maximum bending moment at mid-span, 1.8 times the span length squared divided by 8, so 5.6 kN per meter. And now we have the value that we need to do the design for biaxial bending. So we start now with the ultimate limit state of biaxial bending. So this is the situation. This is our beam. Our beam is inclined by 30 degrees because the roof is inclined by 30 degrees. So the load P 1.8 that we calculated before is the load applied in the vertical plane. So this is, if you want, this is the bending plane, and the bending plane, as you can see, is not it does not contain the symmetry axis of the cross section, meaning that we have biaxial bending. So what we can do, we can decompose the load into two components. If you remember during when you studied biaxial bending in structural mechanics, you studied that one possibility was to use the superposition principle. So basically to decompose the bending moment of the load into two different loads in the perpendicular planes. Then to find out the two different bending around one axis and around the other one, and then to superimpose it. This is what we can do also here with a small modification which we will see later. So, for example, the P, the vertical load, we can decompose into the component along the Z star axis. So this will be P times cos 30 degrees, so this angle is 30 degrees, so 1.6 kN per meter. And then the other component is P times sin of 30 degrees, which means 0.9 kN per meter. So the bending moment associated with the load P will be this vector here. Also the bending moment can be decomposed into simple bending action, my asterisk. So my asterisk is the bending moment times cos of 30 degrees, so 5.6 times 0.87 is 4.9 kN per meter. And the bending moment acting along what we call mz asterisk, so the bending moment acting in this plane here, which will be 5.6 times 0.5, so 2.8 kN per meter. So we can decompose directly the bending moment, so this biaxial bending, to the superposition to simple bending, one around the y asterisk axis, which is what we call mz asterisk, and the other one around the one bending moment, this mz asterisk, it has as a neutral axis this one, y asterisk, while instead the my asterisk bending moment has z asterisk as the neutral axis. So the regulation said that we need to check biaxial bending with this design inequality here, where sigma m y d asterisk is the basically the stress due to one bending moment, and sigma m y d asterisk is the stress demand due to the other. So sorry, sigma m z d asterisk is the stress demand in the other due to the other bending moment. So we need to calculate the two cross section modulus. So the wy asterisk bh squared divided by 6. So sigma my d asterisk is my divided by wy. We get a certain value. Then we do the superposition with the other bending moment, where we have the cross-section modulus h times b squared divided by 6, and sigma m z d asterisk is basically 5.8. So what we've done now, we have basically decomposed this biaxial bending into two simple bending problems. In one case we get one sigma of 6.1 Newton per square millimeter, in the other case a sigma of 5.8 Newton per square millimeter. Now we need to calculate the strength capacity, so the strength, the design strength. The design strength is basically given by this coefficient Kh, which is the size effect, is equal to 1, times K mod equal to 0.9, K6 equal to 1, and Fmk depends on the strength class, divided by gamma m. So 9.6, and then we have this coefficient Km that we have to multiply here the ratio between the strength demand and the strength capacity. In the end, this is our design inequality. So 6.1 divided by 9.6 plus 0.7 times 5.8 divided by 9.6 is equal to 1.05, while instead it should be less than 1, meaning that this cross-section does not satisfy the ultimate limit state of biaxial bending. Same thing, also if we swap, you see in this verification, we need to put the Km first here and then here, so the Km changes. In both cases we get the same value, 1.05, which is greater than 1. So we need to increase the cross section because this check, this ultimate limit state check, is not satisfied. So we can think about, for example, keeping the same cross section, increasing the strength from moving from C16 strength to class C18. So instead of 16, we move to 18 as in terms of bending strength. So we increase the design bending strength to 10.8. And we see that by moving from C16 to C18, the check is now satisfied because we move from 1.05 to 0.95, which is less than 1. Both of them are satisfied, and so we have found basically the solution, keeping the same cross section, increasing the strength class. Okay? This is in terms of biaxial bending. Then what we need to do, we need to calculate the serviceability limit state design load and perform the short-term deflection calculation. In this case, we need to refer to this load condition, the frequent or characteristic load condition. In this case, we have again to take into consideration the size 0 load. We don't consider for serviceability limit state the gamma G coefficient. In this case, you see we have all the different components here. So G1 is vertical, G2 is vertical, QS is vertical, QC is vertical. And then we have, in terms of QW1 Z, we have one value, vertical, and QW2 Z is 0.04 kN per meter. We would have also one small horizontal component for QW2 because again the wind is perpendicular to the surface of the roof. So strictly speaking, we have a vertical component and a horizontal component. So the horizontal component, you see this one, fortunately, as you can see here, is fairly slow. We're talking about 0.02. In fact, it's much slower compared to the other load. So for this reason, what we're going to do, we're going to ignore this horizontal component. Even though, strictly speaking, we should consider it. In fact, if some of you have downloaded the presentation last year, you will find other 2 or 3 pages dealing also with this horizontal component. But it was so small that in the end it was just losing time in the end for nothing because it's too small. Then you need to compose all the vectors of the deflection and so on. So I decided for this year just to ignore because as you can see it's much lower. It's 10, well, it's basically 1/10 of each other values. So it's definitely negligible. Okay. So for the short-term deflection calculation, we need to consider only the variable part of the characteristic load combination without the variable loads which are favorable, okay? In order to do the verification. So we need to consider QS, QC, and QW2, because QW1 is favorable. 3 load combinations, as we said before. Strictly speaking, we would have also this Y. So we will have the vertical component, the horizontal one, but the horizontal one we say so little that it's not really worth it to spend hours to find out that the deflection rather than being, I don't know, 17 millimeter is 17.3 millimeter. This 0.3 millimeter doesn't really change anything out of this. Okay? So here are the 3 different load combinations. So first we put QS as a basic action. So we get 0.59 kN per meter. Then we put QC, maintenance, as a basic action. We get 0.56 kN per meter because of course the other value are then multiplied by the coefficient size 0. And then we do QW2Z as a main condition. And we got 0.32 kN per meter. As you can see, load combination 1, this one, governs current design as a disability step, because here we take the maximum one. The maximum one is the one with snow as a basic variable and wind and maintenance as a combination values. Again, strictly speaking, what we should be doing, we should calculate the deflection of a beam like this, subjected to a load Fz equals to 0.59 kilonewton per meter, and the horizontal load Fy equal to 0.012 kilonewton per meter. Okay? So this is our problem. We have a beam, an inclined beam, subjected to a vertical load and a small horizontal component. And we need to find out the deflection. Strictly speaking, we should calculate the deflection under this force, then the deflection under this, and then to do the vectorial sum between the two. But since this one is much lower than Fz, we just say, okay, this one is almost equal to 0, so we just ignore this. Okay? Clear? Okay, so how do we proceed? The problem is that we are again in biaxial bending. So in biaxial bending, how do we calculate the deflection by axial bending? Again, you can use the superposition principle. So you can decompose your load into 2 components. One in this direction, the other one in the other direction. Then you can find the deflection. You will find the deflection here, the deflection here. And then you need to do a vectorial sum of the 2 deflections. The 2 deflections are 2 different planes. Okay, so one deflection is here. Again, this is the cross section. If you get one delta in this direction, another delta in the other one, then you need to find out the vectorial sum, because we are not in, we are again in biaxial metric. So this is what we are doing here. Fz is decomposed in Fzz and Fzy. Fzz is Fz times the cos of 30 degrees, so 0.50 Newton per millimeter, and Fzy is Fz times sin of 30 degrees, so 0.30 Newton per millimeter. Now with this decomposition, we have two simple bending problems. So one is this. So this problem here, maybe better to do it here. So the biaxial bending moment is basically decomposed in the sum of these two simple bending problems here. Okay? So one is bending around the strong axis, and the other one is bending around the weak axis. In this case, we need to calculate the deflection using the formula that we know. So we know the area, we know the length. Shorter deflection, we need to remember that we have to add to the bending component of the deflection also the shear component of the deflection. So what would be the W, let's say WZ star in the short term? So here we would get WZ star ST short term FZ. And here we will get a W Y star did we make it right? No, it's wrong. So WZ star is the one associated to F, so this one. So WZ star ST FZ is the one inducing, is the one due to bending around Z star, and the other one is Y star ST FZ. I think this one probably is not right. Anyway, so those are the bending moment, the second moment of area around y and around z. So this y, this is y asterisk. Let me check because there's something that doesn't seem quite right. So this is y asterisk. So this one. This is z asterisk. It's okay. So z asterisk, this is 0.59 times 87 is 0.5, okay, this is fine. So here shouldn't be fzy asterisk. Should be fzz asterisk here. Zz asterisk because this is y. Yeah, this one should be so I y asterisk f z y asterisk. Because I think we need to correct something. Here should be with this notation here should be f z z asterisk with I y asterisk. And this is W Z asterisk. Yeah, I think this one is wrong. This should be F Z Z asterisk here, and here should be F Z Y asterisk. So please correct this because otherwise there may confusion. We are not correct now because this is an image, so I cannot correct it. So this one must be F Z Z asterisk. Here, and underneath, instead of FZY asterisk.
Abbiamo preso la direzione Z quella centrale.
Sì.
Poi nella direzione iniziale non è questo il caso perché alla fine è molto più però se fosse stata paragonabile in un'altra combinazione di casi, in un'altra direzione, avremmo dovuto assumere quella.
Sì, il problema è che però non si possono sommare, no? Quindi avremmo avuto due condizioni di carico in due piani diversi. Sì, sì.
Però qui avremmo dovuto scrivere da 0,02.
Sì. Ma in questo caso qui era trascurabile. Sì, il problema, the problem is that sometimes you will get the same problem when you are going to design your single solid crystal heating. Sometimes you have loads acting in different planes. So for example, when you have to sum the permanent load with the wind load. Now in this case we could sum the permanent load and wind because they were in the same plane. But in some other cases, you have, for example, for a frame, you have a permanent load, if you have a frame like this. You have a permanent load and there's no load in this direction. You have to do the combination with the wind, which is actually applying this direction, with the seismic action, which is applying this direction. So there you cannot simply sum and find the maximum value, because it's not possible, because they act in different planes. Okay? So this is more complex to consider, because this criteria of the maximum load condition is not so simple. Okay? Also for the seismic, exactly the same, because it's horizontal, it's in a different plane. So some of those are horizontal loads, some others are vertical loads, so there is this problem here. Okay, so we were saying before, please swap these two values here. So f z z asterisk, f z y asterisk, and also here, this should be f the same. So f z z asterisk also here, not g y. I don't know why I did this here.
significare attorno oppure lungo la direzione?
We need to make a convention. What is that? Because we could say, okay, if this is around y, we take y. Or we can say, okay, this is in the z direction. We just decide which one is. In this case, probably the best thing to do is to say this one is z asterisk, and this one is y asterisk. So not around, but along the direction. So if let's say that if this one is z asterisk stfz, this is f. So exactly in this formula we need to change. So in this formula this is okay. We just need to swap this one with this, right? So this should become f z asterisk, and this one is f w z asterisk, right? Should be this way. Okay, there should be. I think there is a problem on the subscript, not a problem on the calculation. Should be this way. If here you just put f z asterisk and here f z y asterisk, then everything should be fine. Okay? Okay? Also here, please put not gy, but put f z asterisk. Also here, not g. I don't know why this is that. Yeah, I can't correct now because this is an image for a non-equation editor that doesn't work anymore. So I will have either to do another equation editor or I can do it right now. So it's clear again what you need to change. So this one becomes f z asterisk, and this gy becomes f z asterisk again. And here f z y asterisk and f z y asterisk. Okay? So it must be the same as we have here. Okay? So the same value of load that you use for both calculating both deflection due to bending and the deflection here. Now also everything is consistent with I y asterisk and I z asterisk. So these are the mechanical properties that we need to use for our timber. So we need to use, just remind you that for the deflection you need to use the Young modulus, parallel, in bending, so this would be 9. And then you need to use the mean shear modulus, 0.56. Those are gigapascal. So when you put in the equation, you remember gigapascal, which means you have to multiply by 10 to the power of 3 to get the megapascal, which are Newton per square millimeter. So, we do the calculation. We find basically 5.0 millimeter in this direction. You see, in this case, the influence of the shear on the deflection is negligible. So, on the total deflection of, let's say, 6 millimeter, the shear counts only as a 0.1 millimeter. So it's negligible because the beam, if you remember, the shear is important when you have big beams and short span. In this case, you have a shallow beam on a long span, so it's not so important. You see that the maximum deflection is actually in the other direction, the other component, so along y, where we have almost 10 millimeter. Y is more there because in the other direction, of course, we have less load, but also the second moment of failure is less in this direction. Okay? So now, based on this number, I can tell you that what we said before is right. So all the numbers are right, provided you change those two subscripts. Okay? So everything is right. Because in fact, you can see that a larger value in this direction here. And then, of course, in order to find the total deflection, you cannot sum those two values because they are in perpendicular plane. So you need to sum as a vectors. So use Pythagoras here. And we found that the total deflection here, in the short term, is 11.1 millimeter. Okay? This is the total deflection. Total deflection that we need to check against the maximum value provided by the regulation. Maximum value provided by the regulation for a roof is the length of the roof divided by 200. No, sorry, divided by 250 in this case, because it's a non-accessible roof. Okay, of course you can also find the inclination, but this is not really important. So, we are checking this, so length of the roof divided by 250, 20 millimeter. So, in the end, this check is satisfied. Okay? Now, if you wanted to consider also this other, if you remember at the beginning, you have another small horizontal component, you have to have another two pages like this to find out that in the end, instead of 11.1, you have 11.3, which is really, I mean, just an important reminder. When you hand in your design report, what is very important is that you comply with ultimate mistake. So, for example, you can't, in a design report that you submit to the building authority, you can't write that you get a sigma of, let's say, 123 against a limit of 120 and more or less is fine. So this is unacceptable. Okay? Either you round it before and you find out that you say, okay, I found 120 and this 120 is not greater than 120, but you can't write in your design report 123 as the, let's say, the design demand, which is more or less 120, so it does not exceed the limit of 120. Because if one day, by chance, the structure should collapse, you could suffer from some problems. Okay? Because formally you didn't satisfy it, because 123 is greater than 120. Of course, we know that from an engineering point of view, we have so many uncertainties, so many approximations that for me, 123, 120 is more or less the same, doesn't make any difference. But again, from a legal point of view, it's better to avoid this. Different is if you get a limit of deflection, let's say of 20, and here you get 21. 21, strictly speaking, is greater than 20. But deflection is a visibility mistake. It's a state from regarding functionality of the structure. So nothing is going to happen if you have 1 millimeter more. Okay? In this case, in your research report, you can also write, your calculation report, you can also write down 21, more or less 20, so the deflection limit is satisfied. Something that instead it shouldn't be for ultimately mistake, for legal problems. Okay? It's clear this? Good. Now we need to repeat the same thing more or less for long-term deflection to take into account also the creep. So in this case, if you remember when we calculate the final deflection, we need to get the final deflection as a sum between the instantaneous deflection due to the frequent load condition and the creep deflection due to the quasi-permanent load condition. So quasi-permanent load condition is the condition you can see here. Frequent load condition is the last one. Psi 2 you can see for maintenance, wind and snow is 0. So basically this means that when we calculate the creep deflection, we shouldn't consider any variable action. So the creep deflection will only be due to the permanent action. Okay? So these are the value of the loads, G1, G2, QS, QC. Again, we have this QW1Z, QW2Z, and QWYZ. QW1Z is not considered because it's basically favorable. We should consider this only if it was so big to basically cancel out all the permanent loads. Suppose that here you had like instead of minus 0.25, you had minus 2. With minus 2, in this case, you have to do, okay, minus 2 is larger than G1 plus G2. So G1 plus G2 is 0.6, minus 2 is minus 1.4. So in this case, you should consider only QW1. Because it's negative, but it's greater than the sum of the positive value. But since in this case, is smaller than the sum of the positive value, you just ignore it. We just use this other two here. And again, we said before, we can use the vertical component 0.04, or we can ignore the horizontal component because it's very small. So, instantaneous load calculation will be calculated under these 5 loads. We have 3 load combinations. Now, of course, again, it's always the same. Permanent load combinations. We have only this. So, the long-term deflection is composed by 2 parts. The short-term deflection due to characteristic loads, plus the creep due to the quasi-permanent load combination. The short-term deflection due to the characteristic load condition is the sum of the short-term deflection due to the permanent loads and the short-term deflection due to the variable loads. The short-term deflection due to the variable loads was given by 11.1 millimeter, which we calculated before. The short-term deflection due to only permanent loads, since the sum of the permanent load is 0.65 kN per meter, applying the Z direction, and since GK is parallel to FZ, we can use the superposition principle to calculate immediately this quantity, WST of only GK. So we can do this proportion. The deflection due to the permanent load divided by the deflection due to the load condition, so due to the variable load, is basically equal to the ratio between the permanent loads and the variable loads. So if we just replay here, 0.65 divided by 0.59 times 11.1 is 12.2 millimeter. Just not to have to do again all the calculation. We just use the superposition principle. Now we calculate the creep deflection due to the quasi-permanent load condition. This will be the Kdef, which is the creep coefficient of timber, times the deflection due to the quasi-permanent, the instantaneous deflection due to the quasi-permanent load condition. Psi 2 we said that are 0 for any variable load. So in the end we have only G1, G2, and again the short term deflection due to the only permanent loads is 12.2 millimeter, the one we have just calculated. Kdef, the creep coefficient, depends on the service class. We said that in this garage, since this is an indoor condition, but it's not heated, it's a service class 2, so creep coefficient 0.8. So in the end, the creep deflection is Kdef 0.8 times 12.2, so 99.7 millimeter. Now we do the sum of all this load, all this deflection component, 12.2 plus 11.1 plus 9.7, 33 millimeter of total deflection. We need to compare this 33 millimeter of total deflection with the basically limit of the span length over 200, which is 25 millimeter. So, as you can see, 25 the limit, 33 the value, so the long-term deflection control is not satisfied in this case. So we need to increase a little bit the size of the purlin from 12 times 20 we move to 14 times 20, for example. So we have to, strictly speaking, we have to reassess G1, 0.22, all the geometrical properties, all the second area, second moment of area. The short angle deflection this time becomes 5 mm in the z direction, 6 mm in the y direction. Using Pythagoras we get 7.8 of total deflection. This is instantaneous deflection. And again, for the permanent load, again we can do like before, we can calculate the short term deflection due to only permanent load, which is 8.8 mm, smaller. Use the same formula to calculate the creep component. So again, we use 8.8 mm, and if we multiply by the creep coefficient, KF, we get 7.1. So we do now the sum of all the different components. 23.7. Okay, this one, please remove. Just cancel. This doesn't matter anything actually, because this was there from the presentation before where I was doing the composition, so this one is not needed. And now the long-term deflection control is satisfied. Okay? Just to remove the curve, then it's fine. Okay. Now, other checks that we need to do to complete the design are shear strength. So for this shear strength, first of all, we need to calculate the strength amount that ultimately is in shear, which is 4.5 kN. And we need to compare this. Well, we need to calculate the maximum shear stress, and to compare the maximum shear stress with the shear strength of the beam. So, the value of the shear is 4.5 kN. We need to decompose 4.5 kN in z direction 3.9 and in y direction 2.3. Then we calculate the area, the shear area times this reduction coefficient to take into account the problem of crack, shear crack. So it's 2/3, so 1.9. So maximum shear stress is 3 divided by 2 times the shear divided by Kf times A, 0.31 Newton per square millimeter. This is along Z, this is along Y. And we need to go in the two directions because of course we have biaxial bending. And we need to compare these values, so the maximum value is 0.31 with the value of the design strength in shear. Design strength in shear is 2 Newton per square millimeter. Those are the value, gamma m, and the value of the shear, 3.4. Then, since you have two shear stresses, one in one direction, one in the other, what we can do, we can calculate basically as a vector the resultant. So the square root, using Pythagoras, we find out 0.36 of total shear, which is by far less than the strength, 2.2 Newton per square millimeter. So the shear strength check is satisfied. Then we need to do the bearing strength, so we need to do the verification of the support of the beam against compression perpendicular to the grain. again we consider as a restraint reaction the value of 4.5 kilonewton. This is the design inequality. So the compressive stress perpendicular to the grain must be less than the resistance of compression perpendicular to the grain of the beam. Again, we have to consider in this case only one component, so the component along the Z star axis, so 3.9 kilonewton. We need to find, of course, what is the minimum bearing strength necessary to make sure that we won't have any failure in compression perpendicular to the grain. So, according to Eurocode 5, we can consider an effective bearing strength which is greater than the actual bearing strength. So, should be the effective bearing strength would be the actual bearing strength plus 30 millimeters, but in any case should be less than LB plus LB. So if LB is less than 30 millimeters, the maximum would be twice LB. So basically we start assuming that the bearing strength would be less than 30 millimeters, and so the limit is twice LB. So this is the effective bearing strength that we can consider in our verification. So the sigma will be the restraint reaction here, divided by B, the breadth of the beam, times twice LB. So the reason why we consider, if you remember, I told you, the reason why the regulation said we can consider a larger bearing strength is that in the reality, in a situation like this, the strength, if you have a situation like this, the strength is larger than if you have a situation like this. So in other words, this fiber of wood here in some way helps also the resistance of this fiber here. While instead, if you wouldn't have any fiber of wood here, then the strength here would be lower. Okay? It's like thinking about testing, for example, if you have a piece of wood, one thing is if you test in compression perpendicular to the grain, the piece of wood in this way. Another thing is to test a longer beam in this way. Okay? So in this case, of course, you have you get much an earlier failure than in this case here. So in this case, when you push down, you have also the contribution to push down this. You need also to pull down those fibers here. When instead here you need just to pull down the fiber there underneath. That's load. Okay? So the two loading scenarios are quite different. So for this reason, the regulation said that here we can consider also a bearing length twice as much as the actual length, supporting length. So, in the end, we don't know yet what is the value, the minimum value of the bearing length here. So we can consider LB as an unknown. We know T, D, Z, asterisk, we know B. So in the end, you see you get that this shall be equal to 27.8 divided by twice LB. So K6 is equal to 1, K mod is 0.9, FC 90K is 2.2, this is the compressive strength of wood perpendicular to the grain. Gamma M is 1.5. So in the end, FC 90D becomes 1.3 Newton per square millimeter. KC 90 can be conservatively assumed equal to 1, even though for solid timber would be 1.5. So, in the end, 27.8 divided by LB must be less than 1.3. So from this design inequality, we can get LB. So LB shall be greater than 10.7 millimeter. So we just 1 centimeter of support is enough to make sure that we won't get any failure for compression perpendicular to the grain. Last check that we have to do concerns the lateral torsional buckling. If you remember last time by talking about the blue lapin, that was by far the most severe design criterion. In fact, if you remember, we have to put some braces because otherwise we wouldn't be able to satisfy this check. In the end, we had any way to increase the cross section because otherwise it was not satisfied. So in this case, let's go to see what's happened. This is our case. So the first question we should ask to ourselves is, above those pyramids, there is a layer of boards which are basically connected to this pyramids with some nails. Okay, so we have this flooring, roofing, we could call it, inclined. Now, does this flooring or roofing, as you want to call it, made from single boards, provide an effective lateral restraint for the pyramids? This is the first question we should ask ourselves. So what do you think? By having this layer of boards, one single layer above here, is it enough to say that this upper fiber of the purlin is restrained against lateral movement?
Maybe not.
Maybe not. Why not?
Because it go not so much.
Not so much. Yes, well, we have to consider that those boards are narrow, because usually the boards are not very big, they are fairly narrow, and they are connected with a couple of nails, so the connection is quite weak. So we should ask ourselves, is that enough to prevent this kind of movement, like this? This would be that if you have lateral torsional buckling looking down, you would say all this purlin is buckling this way. So are those layers enough to prevent this? Well, if this was completely plain, if this was not a roof but a floor, so a horizontal floor, what would happen is that all the purlins could actually buckle. So the half this way and also all the other half. So everything would buckle in this way. Why they would buckle? Because these boards, as I said before, are narrow. So here you have, for example, one beam, another purlin, and so on. Is those planks act as a pin element. Why as a pin element? Because they are narrow and they have small nails around. And then, of course, you don't nail one plank which is 5. I don't remember the length of this, but the length of this will be 3.5 meters. Usually the plank is not 3.5, it's a little bit less. So it could be also discontinuity. So in the end, this one is not enough to prevent a global buckling like this. Because what would happen is that all the pyramids buckle all together, and those planks do nothing else than basically making all of them to buckle together. So rather than buckling only one, you get all of them buckling together. This is the only effect of these boards. Because again, those boards are narrow boards. Something like this, with maybe sometimes one nail, sometimes two nails. Okay? So they act as a truss, as an axial force, that's it, nothing more. If this was a roof, sorry, if this was a floor, a plain floor. However, in our case, they are inclined, the two floors are inclined. Here we have two you have something like this. So we need to ask ourselves, if here I connect, those are the purlins, and here I have my joist, are those purlins able to prevent this buckling, this movement of this purlins in this way? Well, this one, to buckle here, it should lift up also the other pitch of the roof, because they are not in the same plane. So in some way we could say that this roof, this layer of boards will provide some restraint. For sure it's more restraint on the roof than the one that we would have on the floor. This is better, it's better restraint, but how effective is it? Very hard to say. Because, of course, again, these planks are very, very narrow, and so we don't know how effective they can be in preventing this total lateral torsional buckling. For sure, we could make something of effective, you see, by connecting, if this is one layer of boards, this is another layer of boards, we could think about connecting with some nails, basically, with basically a piece of steel, the two pitch together. If you connect the two pitches together with some nails with a piece of steel, for sure it will be difficult that this member here can buckle in this direction because there is this restraint on the other one. So this one to buckle up, for this member here to buckle in this direction, it would mean that also this should be uplifted, and perhaps also this beam here should be uplifted, which is not so simple. But again, to say how effective is this restraint is very hard to say. So, to avoid problems, since it's very hard to say, okay, this provides a good restraint, this doesn't provide a good restraint, it's very hard to say. My suggestion, even though I'm sure that it will be difficult for this member here to buckle, if you do a connection like this, but not to get in any trouble, I would say that conservatively it's better to do a design also for lateral torsional buckling. Okay? This is it's very hard to say. This is something which is very different from pure science, you know. In this case, from the mathematical point of view, say that this buckle, this doesn't buckle, will involve such a complex problem that it's better to try to think about, try to find a simple solution. The simple solution is to do a conservative assumption that there is no restraint, and to see if, in this case, unlike what we saw for the design of the Brulan beam, we can get this verification satisfied. Because, as an advantage with what we saw in the last work example, here we don't have a very extremely long beam and very deep. Remember, we said before lateral torsional buckling is a big problem if we have a narrow beam and very high and long. In this case, we have a kind of squat beam, more or less 14 by 20. And the length, of course, the length is important compared to the depth, but again, the depth is not very high. So we can expect less trouble when checking the lateral torsional buckling in this case. Another problem is that the formula that the regulation provides for lateral torsional buckling, Euro code 5, are formula for simple bending moment. Well, instead, in this case, we have flexural buckling. Sorry, we have lateral torsional buckling on a biaxially stressed beam. So in the beam, we have a biaxial bending moment. So this is a very hard, very difficult problem to solve. We should ask to Professor Luogo how to do it, because of course, usually you study the flexural buckling when you have lateral torsional buckling when you have simple bending. But if you have a biaxial bending, it's much more complex. So also here we don't have a simple formula, and the only thing we can do is to basically check. This is my suggestion: is to check separately lateral torsional buckling first around Y, then we check around Z, and then we combine together the stress ratio that we find in two cases. Okay? Knowing and accepting that this is a very rough approximation. If we tell that we do it this way to Professor Long, we say that we are completely wrong. Prof is right. But rather than, solving a complex differential equation, like here, again, from a biaxial bending problem, I think this is the only thing we can do to get a kind of practical and engineering solution in this case. So just to make it simple, we have already seen, if you remember, on Monday quite extensively how to do it with lateral torsional buckling if you have just simple bending. So the formulas are again exactly the same. The only difference, the only new here compared to what we have done on Monday is that we need first to check the lateral torsional buckling around Y, and then to do exactly the same check around Z, because we have biaxial bending moment. And use this criterion, which is a criterion which was, if you want, was invented by me, because you cannot find anything on either the books or on the regulation. Another option could be, for whom of you are attending the other course, to ask to the other professor how to do in this case. So how to find the verification in the case of biaxial bending moment and flexural lateral torsional buckling. Okay? Otherwise, I would suggest to do it this way. So if you remember last Monday, for simple bending, we did this check here. So sigma m y d divided by k crit times f and d less than 1. The idea is that since we have biaxial bending, first we calculate this ratio, then we calculate this, and the sum shall not exceed 1. This way we take away the kind of average way, the fact that we have a biaxial bending, not a simple bending. Now, without losing too much time, by now you know how to do it, I would say. Don't need to go too much into that. Just remember you need to check the effective length. The effective length, since we have a uniformly distributed node, is 0.9 L plus twice the height of the beam, the depth of the beam. In this case, if we have a shallow beam, it's not a big increase. Then we calculate sigma MYD, which is the normal bending stress without any buckling, 5.3. Sigma MZD in the other direction, 4.3 megapascal. Then KH1, K mod 0.9, gamma M 1.5, K6 1.0, FMYD 9.6 Newton per square millimeter. And then, of course, the best thing here to do is to have an Excel spreadsheet, to implement all the formula in an Excel spreadsheet. You would see, for example, that talking about lateral torsional buckling around Y, so if this is our beam, now we are talking about beam Y. We are talking about lateral torsional buckling in this direction, this way. So lateral torsional buckling this way, you see at the end, you have a K crit reduction coefficient of 1. Reduction coefficient of 1 means that lateral torsional buckling is not a problem. So it means that we don't have to reduce by any factor our strength because of lateral torsional buckling. This is because you see the relative slenderness ratio is very low. And so K crit Y equal to 1. Then we do exactly the same thing for lateral torsional buckling around Z. So Z is this axis here. Okay? So now we consider lateral torsional buckling in this way. Okay? This way and this way. Around the other axis. So lateral torsional buckling around Z, we calculate again the critical sigma 197, the relative slenderness ratio 0.25, which is less than 0.75. So again, K crit, this reduction coefficient for lateral torsional buckling is 1. So again, also in the other direction, lateral torsional buckling is not a problem. So you see, we discover in the end, without having to say that yes, we have we have or we don't have a good restraint, we discover in the end that for this pin lateral torsional buckling is not an issue. So it's much better in a design report to write down that you've done this verification here rather than stating that your timber flooring was enough to provide a good restraint and so on. In this case, you see, when you sum the report, you get actually 1, which is equal to 1. So if you sum this, you get 1. 1 is equal to 1. So this means that lateral torsional buckling is not a problem for this type of pin. Last thing, just to conclude, how could have been, suppose that this lateral torsional buckling was a problem here, and we didn't want to change the size of the pin. What could have we done to make sure that this layer of boards could provide some restraint? The idea is that rather than using narrow boards, we could have used larger boards. For example, sheathing of plywood. Remember, we studied the two-dimensional panels of plywood. If you use plywood, so if you use bigger boards, wider boards, in this case it's clear that this layer of sheathing provides an effective flooring. Why? Because you see here, if you have a wider panel, of course you can have to get a lateral torsional buckling of the beam, we could have a distortion of the panel, which is very likely because the panel has an in-plane resistance. So the other option, if you want to make sure that you don't have any lateral displacement, is to replace the layer of narrow boards with a layer of plywood sheets or OSB sheets. So something which is not narrow and long, something which is wider and longer. Okay? So this panel are usually 2.4 times 1.2. This could have been the option. Okay, any question? Something that is really needed because otherwise you don't survive because the time is late, as you can see. Yes?
With this type of we actually